On April 6, 2026, something happened that most people watching the live broadcast probably missed. Four astronauts aboard the Orion spacecraft, somewhere around 252,000 miles from Earth, reported seeing flashes of light on the darkened surface of the moon. 6 of them, to be exact. When Mission Control in Houston received that transmission, there were audible screams of delight in the science evaluation room. Not because they saw something unexpected, but because they finally saw something that scientists had been desperate to document with human eyes for decades. But what those flashes reveal about the moon is making some researchers genuinely uncomfortable about our plans to put people there permanently. Let me explain what Artemis II actually discovered during those 10 days in space. Because the official press releases tell you about the records they broke and the beautiful photographs. What they do not fully explain is what the crew observed that has direct implications for anyone who might one day live on the lunar surface. First, some context. Artemis II launched on April 1st, 2026, from Kennedy Space Center in Florida. The crew included NASA astronauts Reid Wiseman as commander, Victor Glover as pilot, and Christina Koch as mission specialist, along with Canadian Space Agency astronaut Jeremy Hansen. This was the first crewed mission to the moon's vicinity since Apollo 17 in December of 1972. More than 53 years of silence finally broken. The mission lasted nearly 10 days. They did not land on the moon. They did not even orbit it in the traditional sense. Instead, they flew a free return trajectory that took them around the far side before slingshotting back toward Earth. The closest they got to the lunar surface was about 4,067 miles. A vantage point that gave them something entirely different from what the Apollo crews had. Not the close-up, surface-level perspective of men who had landed. Something wider, a view of the whole moon pole to pole, filling their windows at once. Victor Glover made history as the first black astronaut to travel beyond low Earth orbit. He had previously spent 168 days on the International Space Station as part of the SpaceX Crew 1 mission, serving as flight engineer on expeditions 64 and 65, and becoming the first black astronaut to complete a long-duration stay there. Christina Koch held the record for the longest single spaceflight by a woman at 328 days on the ISS before this mission. Jeremy Hansen had never been to space before, making Artemis II his first flight, and he became the first Canadian ever to leave Earth orbit. Reid Wiseman, at 50 years old, became the oldest person to travel beyond low Earth orbit. He previously spent 165 days on the International Space Station in 2014 as part of Expeditions 40 and 41. And here is something worth sitting with for a second. These were not people handed a historic mission as a token. These were some of the most experienced, technically sharp operators NASA had. Every single one of them carried a story that runs deeper than the headlines. Wiseman spent years as chief of the astronaut office before stepping back down to get back in the rotation for this flight. He did it as a widower, raising 2 daughters after losing his wife Carol to cancer in 2020. He wanted this mission badly, and he earned it the hard way. That kind of personal weight travels with you into orbit. This was not just a symbolic crew. These were people selected specifically because NASA needed operators who could handle unexpected situations without constant guidance from Earth. The 40-minute communication blackout when they passed behind the moon proved that capability in real time. For those 40 minutes, there was no Houston, no ground support, nothing but 4 people in a spacecraft navigating the far side of the moon in complete silence. And from that position, from that distance, nobody had reached in over 5 decades. They saw things no human had ever witnessed before. Start with the Oriental Basin. This is a massive impact crater, roughly 580 miles across, sitting right on the boundary between the near side and the far side of the moon. From Earth, only the outer mountain rings are visible, with the basin interior remaining largely hidden. The Apollo astronauts caught glimpses during their missions, but the geometry of those earlier flights was deliberately planned, so the near side stayed illuminated during their close approaches, which meant the Oriental region was almost always in darkness or just out of frame. The Artemis II trajectory changed that. NASA had organized 30 scientific targets for the crew to observe during their 7-hour flyby, and the Oriental Basin was among them. This time, the lighting conditions were right. The crew photographed it extensively, describing its structure and color variations in real time to scientists back on Earth who were following along from Johnson Space Center. Why does this matter? Oriental is one of the youngest major impact basins on the moon, formed about 3.8 billion years ago when something massive slammed into the lunar surface. The rocks surrounding it likely contained material excavated from deep within the moon's interior during that collision. Understanding Oriental in detail means understanding the moon's geological history in ways that orbital photographs simply cannot provide on their own. You need a human brain interpreting what those eyes are seeing in the moment. And that turns out to be enormously valuable. Human eyes are remarkably good at picking up subtle color nuances, texture shifts, brightness differences that cameras set to predetermined exposure settings might capture differently. Scientists on the ground were receiving observations in real time and adjusting their guidance as the crew reported what they were seeing. This was not passive sightseeing. This was active scientific fieldwork conducted from 4,000 miles above the surface. The kind of field geology that planetary scientists spend careers trying to do remotely with robots. And that takes on a completely different character when an actual human being is the instrument. Now, about those flashes. The moon has no substantial atmosphere. On Earth, small meteoroids burn up long before they reach the ground. The friction creates heat, the objects vaporize, and we see a brief streak of light we call a shooting star. But on the moon, there is nothing to slow these particles down. Even objects the size of a marble hit the surface at thousands of miles per hour. When they do, the kinetic energy is released instantly as a flash of light, less than a second, but visible if you know where to look and if the conditions are right. The Artemis II crew was specifically tasked with watching for these impact flashes during the solar eclipse portion of their flyby. For nearly an hour, as the sun hid behind the moon and the lunar surface fell into complete darkness, the crew had a view that no human had experienced before, and they counted 6 meteoroid impacts. 6 tiny white and bluish-white pinpricks of light on the black face of another world, each one marking the moment a piece of the solar system collided violently with the moon. 6 might not sound like much, but consider the context. The crew was only watching for a portion of that window. They were 4,000 miles away, which limits what is even detectable. And they were human eyes doing the work, not a dedicated monitoring system with sensitive cameras running continuously. Professional programs on Earth have been tracking impact flashes telescopically since 2006, logging more than 400 confirmed events over nearly 2 decades. Those programs watch the entire lunar disk, from the ground, through an atmosphere. The fact that 4 people watching from a spacecraft in deep space saw 6 impacts in one viewing period was something that genuinely surprised the scientists following along in Houston. Kelsey Young, the mission's lunar science lead, said at a press briefing the next day that she did not know if she expected the crew to see any on this mission, and that the surprise and shock on her face was very real. She described audible screams of delight in the science evaluation room when the crew first reported what they were seeing. Peter Schultz, a professor emeritus of geological sciences at Brown University and one of the leading experts on lunar impact processes, put the implication plainly. The daily flux of meteors should be monitored more closely in the future before a lunar base is established. Think about what that actually means in practical terms. NASA is planning to build habitats, power systems, scientific equipment, and eventually a sustained human presence on the moon. All of that infrastructure will be exposed to this bombardment continuously with no atmosphere to shield it. We have known about the impact hazard in the abstract for a long time, but having trained human observers confirm multiple events during a brief window from a position that limited their detection range considerably raises serious questions about whether our current risk models are accurate enough to design long-term structures around. The flashes the crew observed are now being cross-referenced with data from satellites orbiting the moon to extract measurable details. Scientists want to correlate the timing and brightness of what the astronauts saw with orbital imagery to determine the size of the impactors and whether new craters were formed. The goal is to build a much clearer picture of the actual impact flux at the lunar surface, not an extrapolated estimate, but data grounded in real human observation from a unique vantage point. When future missions have seismometers deployed near the landing zones, and when those seismometers record vibrations from an impact that a camera or a crew member also witnesses visually, researchers will be able to measure exactly how energetic those strikes are. Not just whether they happened, but what kind of structural damage they could cause to a habitat or a pressurized vehicle sitting on the surface. That is the kind of data you need before you commit to a design. But the impacts were not the only phenomenon the crew documented on the darkened lunar surface during that eclipse period. They studied the solar corona. When the moon completely blocked the sun, a luminous halo of plasma appeared around the lunar edge, extending outward in delicate streamers and plumes. This is the corona, the sun's outermost atmosphere, usually invisible against the brightness of the solar disk. The crew had nearly an hour to photograph and observe it from a position that no human had ever occupied before, and scientists are still analyzing the imagery to extract information about coronal structure that is difficult to measure from Earth-based solar eclipses, which typically last only a few minutes. They also watched for lunar dust. There is a phenomenon called lunar horizon glow, first observed by robotic surveyor missions back in the 1960s. A faint luminescence above the lunar surface near the terminator, the line between lunar day and night. The leading theory involves electrostatic processes. On the sunlit side, solar ultraviolet radiation ejects electrons from the regolith, giving fine dust particles a positive charge, causing them to briefly levitate. The particles then settle back down, creating a subtle glow detectable from certain angles. The Artemis II crew was looking for it. They did not report a definitive sighting, but the data they collected during the observation period will take months to fully analyze. This matters because if levitating dust is more widespread or more persistent than current models assume, it has real consequences for everything from landing zones to the seals on airlocks to the long-term health of anyone spending time on the surface. Lunar dust is not like Earth dust. According to NASA research, lunar soil is composed of rock fragments, single mineral grains, and a dominant glassy component made up largely of agglutinates and impact glass, formed when micrometeorite impacts melt and fuse soil particles together. In mature soils, these agglutinates can account for up to 60 or 70% of the material. The particles are jagged, angular, and electrostatically charged, and they stick to everything aggressively. Apollo astronauts reported that dust worked its way into equipment despite every precaution they took. It scratched visors, abraded suit materials, clogged mechanisms, and was tracked into the cabin even after the astronauts brushed off their suits. On missions that lasted only a few days on the surface, dust was already emerging as one of the most annoying and potentially dangerous factors. A permanent base means living with that dust indefinitely. If it is also actively levitating and circulating, you are not just dealing with something you tracked in. You are dealing with a perpetually present environmental hazard that requires a completely different design philosophy. The views the crew captured were extraordinary. As Orion emerged from behind the moon after the communications blackout, the astronauts saw Earth rising over the lunar limb, a small blue crescent against absolute black. The image called back to the famous Earthrise photograph taken by Apollo 8 astronauts in 1968, but captured with modern cameras that could resolve details simply impossible on the equipment of half a century ago. Victor Glover described it as an unreal view, with stars everywhere, the moon in the foreground, one of the darkest things visible, and deep space behind it appearing almost dark blue, the way it looks from Earth, but with stars still visible throughout. Christina Koch later said the view changed something in how she understands the planet. From that distance, from 250,000 miles away, the borders that occupy so much of our daily argument simply cease to exist. It is just one world, small, fragile, impossibly bright against the darkness around it. She called it an oasis. There is something that always strikes me about that observation. Astronauts have been saying it since Gemini, since Apollo, since the shuttle era. Every single one of them comes back describing Earth differently. And yet somehow, from down here, the view never quite changes the way they say it should. Maybe you have to see it to actually feel it. Now let me tell you about the heat shield, because this is where things get genuinely complicated. During Artemis I, the uncrewed test flight in November 2022, the Orion capsule's heat shield came back damaged in ways that surprised the engineers. More than 100 locations showed unexpected erosion, cracking, and charring that the computer models had not predicted. The shield is made of a material called AvCoat, an ablative substance derived from Apollo-era technology. But when it hit Earth's atmosphere at around 25,000 miles per hour, gases generated by the extreme heating got trapped inside the material. The material lacks sufficient permeability to vent those gases naturally, so internal pressure built up until the shield cracked, ejecting fragments of the ablative layer. NASA spent years investigating this. Some engineers had serious concerns about flying a crewed mission before the design was modified. Others argued that the underlying structural layer would remain protective even if the ablative surface degraded beyond models, keeping temperatures inside the capsule safe for crew. In January of 2026, NASA Administrator Jared Isaacman personally convened a review that brought together the agency's heat shield engineers, the chair of the independent review team, senior human spaceflight officials, and outside experts, including invited critics. After that review, Isaacman declared full confidence in the spacecraft and its heat shield, stating that the decision was grounded in rigorous analysis and the work of exceptional engineers who followed the data throughout the process. The agency approved Artemis II to proceed, but NASA did make one significant change to the re-entry flight profile. The original plan for Artemis II had called for a skip re-entry, where the capsule would briefly dip into the atmosphere, generate lift, skip back out, and then plunge in again for the final descent. NASA's investigation determined that this extended, multi-phase heating exposure was allowing gases to build up inside the avcoat layer in ways that caused the cracking seen on Artemis I. For Artemis II, they replaced that profile with what NASA called a lofted entry, a steeper trajectory that descended faster and at a sharper angle. This shortened the spacecraft's exposure to the most extreme re-entry temperatures from roughly 20 minutes on Artemis II down to approximately 13.5 minutes, reducing the window in which those trapped gases could accumulate and cause the shield to crack. The trade-off was harder physical forces on the crew. Wiseman described being under 4 Gs for about 13 minutes, a significantly more demanding experience than the skip profile would have produced. But the engineers considered that an acceptable cost to protect the shield. Did it work? Wiseman said at the post-flight press conference on April 16th that he and Glover may have seen 2 brief moments of what looked like char loss during the hottest phase of re-entry. They spotted some material loss on the shoulder region where the heat shield meets the capsule walls, but the overall assessment from the crew was positive. Wiseman said the shield looked wonderful to 4 humans examining it from what they could see, and that NASA would go over every atom on that heat shield in the detailed post-mission analysis. That analysis will directly shape what happens next, because Artemis IV, currently the target for the first crewed lunar landing in 2028, will still use the Orion capsule to bring its crew home through that same atmosphere. Whatever NASA learns from studying the Artemis II shield will be the foundation for every crewed lunar return mission that follows. There is no margin for error on that particular problem. One more thing the crew did that did not get as much attention as the records and the crater names. They tested the Orion spacecraft systems in ways that simply cannot be replicated on the ground. For nearly 10 days, they operated life support equipment, navigation systems, propulsion controls, and communication links under real deep space conditions. They performed manual piloting demonstrations, physically flying the spacecraft and testing how it responds to human input across different steering modes, evaluating its handling at distances where automated systems are valuable, but human override capability might one day be critical. This is not just a procedural box to check. Future deep space missions to Mars will face communication delays that can reach up to 24 minutes in each direction, depending on the planet's positions. In an emergency, waiting that long for a round-trip exchange with ground control is not an option. The crew has to be capable of making their own decisions with whatever information they have on hand. Artemis II was partly a demonstration that Orion can support that kind of crew autonomy and that the people flying it can exercise it under real mission conditions. The laser communication system, known as O2O, and developed by MIT Lincoln Laboratory in collaboration with NASA Goddard Space Flight Center, performed beyond expectations. The system uses infrared lasers to transmit data at speeds up to 260 megabits per second. For comparison, the radio systems Apollo relied on could take several minutes to send a single photograph. The O2O system transmitted over 100 gigabytes of data in just its first few days of operation, including high-resolution video and images from the lunar flyby sent back to Earth in something close to real time. That capability matters for future missions in ways beyond just having better photographs. A communication link fast enough for live video conferencing means doctors on Earth could consult with a crew in real time during a medical emergency on the Moon or on the way to Mars, It means mission planners can review observations together with the crew the moment they are made, rather than waiting hours or days for data to arrive. The gap between what is possible and what was possible during Apollo, in terms of human connection at those distances, is extraordinary. After splashdown on April 10th at 8:07 in the evening Eastern Time, the crew was recovered by the USS John P. Murtha in the Pacific Ocean, about 40 to 50 miles off the coast of San Diego. There was a brief communications issue between Orion and the recovery teams immediately after splashdown, which delayed the initial approach to the capsule. Once communications were restored, Navy divers and NASA recovery personnel reached the spacecraft, helped the crew exit, and transported all 4 astronauts by helicopter to the ship for medical evaluation. From there, they flew to Houston. By April 16th, they were standing at a press conference at Johnson Space Center, healthy, articulate, and clearly still processing what they had been through. Wiseman was asked about Carroll Crater. He told reporters he had been so busy since landing that he had not even had time to look up at the moon yet. The naming itself happened during the flyby on April 6th, in the emotional aftermath of breaking the human distance record. Jeremy Hansen, speaking to Mission Control, proposed naming 2 newly observed craters. One after their spacecraft, Integrity, the other he dedicated to Carol Taylor Wiseman, Reed Wiseman's wife, who had died of cancer in 2020 at the age of 46. He described her as the spouse of Reed and the mother of their 2 daughters, and said she had dedicated her life to helping others. The crew, floating together in zero gravity around 250,000 miles from Earth, held on to each other. It was the kind of moment that makes you realize that the biggest missions always carry the weight of something personal alongside the weight of history. So what did Artemis II actually show us that has not been fully explained in the celebration? Not secrets. The data is being released. The mission was documented with a thoroughness that Apollo never had. But the tendency in these moments is to focus on the triumph and treat the complications as footnotes. The heat shield performed well enough to bring the crew home safely, but detailed analysis is still underway. NASA will need every piece of data from that re-entry before it can confidently declare the design ready for repeated crewed lunar missions. The 6 meteoroid flashes were thrilling to witness, but they also represent a data point that planetary protection engineers are going to be thinking about carefully for years. Infrastructure on the moon, whether it is a fuel depot or a habitat or a mining operation, will be exposed to a bombardment that is constant, energetic, and poorly characterized at the sizes and frequencies that matter most for structural design. The Oriental Basin was observed under unprecedented conditions, and that is genuinely remarkable. But what that observation ultimately contributes to science depends on months of analysis that has barely begun. The laser communication system worked beautifully and will reshape how future missions stay connected to Earth. But the radiation data the crew's dosimeters were collecting, the organ-on-a-chip biomedical monitoring, the sleep pattern records and cardiovascular readings, all of that is still being processed. Those measurements will directly inform how NASA approaches crew selection and mission duration limits for deep space travel. Not just for the moon, but for everything that comes after. And that is really the point of Artemis II, if you think about it in the right frame. This was not the finish line. It was a field test conducted at the edge of human reach, designed to find the things that are still unknown so that the missions that actually land on the lunar surface, that actually build something permanent up there, have a real foundation to stand on. NASA is planning a crewed landing with Artemis IV, targeting 2028 at the lunar South Pole near permanently shadowed regions, where water ice is believed to be locked in craters that sunlight never touches. If that ice can be mined and processed, it becomes oxygen for breathing and hydrogen for rocket fuel. The moon stops being a destination and starts being a base of operations for everything beyond it. A refueling stop, a staging area, a place where humanity practices being a multi-world species before attempting the vastly more difficult step of Mars. But none of that happens without the data from Artemis II. None of the infrastructure design decisions, none of the heat shield revisions, none of the radiation shielding improvements happen without the answers this mission is still in the process of providing. The mission is over. The analysis has barely started. Artemis II proved that humans can travel to the moon's vicinity and return safely after 53 years away. It proved that the core systems of Orion work in deep space. It produced scientific observations that are already generating research. And it set records that will stand until Artemis IV surpasses them. But the most important things it did were quieter than any of that. It reminded us what human observers can contribute that no robot can replicate. It gave us an honest look at the challenges still between us and a permanent lunar presence. And it told us clearly that the next step is not a symbolic visit. It is building something that lasts. The footprints Apollo left are still there. The moon preserves them perfectly. What we put there next is going to be a lot harder to leave behind and a lot harder to get right. That is worth understanding before we go. If you made it this far, leave your thoughts in the comments, good or bad. It truly helps the channel grow. Hit like, subscribe for more content like this one, and take a look at the video on your screen that I think you'll really enjoy.